Hi, everybody. This is a new episode of the Physics of Bitcoin show with Giovanni and Stephen. Uh, we are today is September 3. Just change the month. This time is going so fast. 2025, and this is episode number 31. So, just a little introduction about what the show is about, like we do always. Basically, you have two physicists here with kind of eclectic backgrounds. I was a professor for some time teaching physics, and I changed career, and I became a neuroscientist at Western University. Stephen did several things himself, and first in physics. He has a PhD from Harvard in astrophysics. Then he started to work in the field of computing. He's the guy to ask all the questions about quantum computing and Bitcoin. In fact, in our episode number 5, we did a full show on quantum computing. So, in fact, it's actually one of the best presentation I ever seen on the subject. And so basically, the main idea is that we are using these tools that we learn from being physicists and apply in our career in many different fields with quite good success. When we discovered Bitcoin, we fell in love with it. And of course, being physicists, right, everybody brings in their own angle in understanding Bitcoin. For us, it was important to understand it from a physics point of view, because Bitcoin is very regular, is a system that can be studied with these tools. And in fact, our position is that probably these are the best tools to understand Bitcoin and show all these beautiful regularities that Bitcoin has. Many people ignore it. They say things that are actually can be shown to be supported by our physical understanding of Bitcoin, but mainly these statements like Bitcoin is a network, or like Sailor says is like a city. These are things that actually can be demonstrated by using these are tools developed from physics or analogy from physics. So this is our particular approach. Also, what we see in this show is original research. We don't have breakthrough every single time, but the main idea is to bring new insights. We are trying, every single week to come up with new result, new idea, new ways of looking Bitcoin from many different angles. So probably if you look at all our episodes that are now at 31, you will find probably among the most original insights into Bitcoin that you can find anywhere else. So I know here some of the things we talk are technical and a little bit difficult to follow sometimes, but go back. Sorry for all this noise. Go back to some of these episodes and watch them again. Like I say, for example, number 5 is a great discussion about. In that case, it's not really original results, but at least the analysis is combining, Stephen's expertise in computing and his understanding of Bitcoin that I think is very unique. Anyway, you can also feel free to ask questions. We show this. The show is can be seen on X, on YouTube, on Twitch, and so you can ask questions at any time. Usually answer them at the end of the show. All right. Given the introduction, and Stephen, you can add anything else if you feel like. And we don't hear you, unfortunately.
Right. How about now?
Okay, go ahead.
Yeah, okay. It tends to quiesce itself for some reason. So typically we will present research results and modeling results, and I have a little bit of that today. Occasionally we'll do a report, an overview of other people's work and research. It could be a quantum computing, understanding where that is. It could be a book report on what Sornet has done for his log periodic parallel model. Today is a little bit different. I'm going to present an analogy between Bitcoin and black holes. And you've seen a lot of people write about black holes as an analogy, the idea that it's sucking in the fiat wealth that's around it. I've always been somewhat bothered by that because it's a little bit inaccurate. So I'm going to present a little different view as to an analogy between, in particular, the supermassive black holes, the largest ones, and the Bitcoin bubbles and the way those have behaved. So shall I dive in?
Yes, let's move on.
All right, and then one of the reasons that I'm presenting this today is that Rainier Weiss, and Giovanni knows extremely well who he is.
Yeah, I met him.
Yeah, I'm sure.
And in fact, one time we was together with all these people from MIT and so on, and we were talking about neutron stars, and I made some comments, and the guys were saying, well, we need to have some kind of a course or introduction to this topic, and he said, oh, this guy is very good at it. And I was like, oh wow, like like when you receive a compliment from your dad or something,
Yeah,
I was really happy because he was already like a leader in the field, but eventually, he won the Nobel Prize. So I was really happy about, somebody was Nobel Prize material making even as a short comment about my knowledge of neutron stars. I was very happy about it.
Yeah, indeed. That's wonderful. Well, he just passed away at the end of last month, less than 2 weeks ago. And that got me thinking about black holes and so forth, and about the detection of gravitational waves, which is a research field that Giovanni worked in years ago. Weiss was born in Germany in 1932 and escaped as a child. His parents, eventually brought him to the US. He was a professor of physics many years at MIT and also associated with LSU, which is one of the two sites for the Gravitational Wave Observatory. Is in Louisiana. The other one is in Washington State. It's called LIGO, LIGO. The GO stands for not Giovanni, but Gravitational Observatory. So what I want to present today is this analogy between black holes and Bitcoin, in particular, the supermassive black holes, but I'll start with introducing black holes more generally and gravitational waves. And it took over half a century to detect gravitational waves. Some of the first efforts were with these large aluminum cylinders and other metallic cylinders that they would instrument. There was a guy, Joe Weber, I'm sure Gio remembers him, who was at the University of Maryland, I think, in the 1960s, and he had even claimed to have detections, and they never got verified. We just didn't have instruments.
Now it was so crazy because
he was crazy.
If he was right, basically we will have an explosion, a supernova explosion, almost every day in our galaxy.
Yes.
And
Right.
So but it was interesting because, sorry to interrupt you now. So
no, please go.
His claims motivated a lot of people in reproducing this result, right? Or try to replicate the result. And so they actually built a detector here in United States. And in fact, at LSU, my advisor was the guy that actually built it. And so it was like he was a pioneer. This was the old generation of detectors with these frozen aluminum bars, like 1 ton bars of aluminum. And so, and kind of kick-started the field because if maybe he didn't make the claims, it was going to be some kind of follow-up, and maybe the field will have been started sooner or later, but maybe much later. And so these crazy claims, people knew they were crazy, but they tried anyway. So that kind of started the field of gravitational wave detector. For the audience, Einstein discovered, found them theoretically in 1915. And in the paper itself, it's in German, but if you read the translation, right, he actually claims that this result is very interesting because basically it creates an analogy between electromagnetism, right, where you have an accelerating charge that produces electromagnetic waves. In this case, we have an accelerating mass that produces gravitational waves. There are similarity differences. They travel at the same speed of light and so on. They have, some differences in terms of technical details, but you say, okay, this is beautiful theoretically, but we will never be able to see them. He actually claimed that because he couldn't imagine in 100 years the incredible advancement of technologies like lasers and all kind of things like this, But yeah, we did it. It was like an incredible achievement, but we did it.
So the incredible thing is that it's the 100th anniversary of general relativity being published when the first detection was made. And so it was 10 years ago from this month. And then, the experimental efforts started in the 1960s. And so it took over half a century to detect in 2015. So the gravitational waves that we're now detecting, and abundantly, come from the mergers of black holes and neutron stars, but primarily two black holes, sometimes a black hole and a neutron star, and sometimes two neutron stars. Black holes we categorize as different masses: the stellar class, the intermediate class, and the very most massive ones that we call supermassive. And it's that category of these supermassive black holes that reside at the centers of galaxies. And we think pretty much every large galaxy has a supermassive black hole. It may be less or more active, but it's probably there. Is the best analogy with Bitcoin's bubble behaviors. And I want to talk a little bit about those categories, and then show a chart with all the detections that have been made from these mergers. We're not going to have a lot of equations here, so it's going to be descriptive. But then I'm going to get into the supermassive black hole SMBH growth history and make the analogy with the Bitcoin bubble history. And what we find is that over time you run out of gas. And so, the analogy will kind of break down as time goes on, the analogy with Bitcoin. And for that reason, I think we're going to need another astrophysical analogy to extend things. And I've built an analogy around dark energy, and that will be next week. And then I'll close with the latest log periodic power law studies that I've just run in the last day or two for Bitcoin and also for strategy MSTR. And Giovanni, feel free to jump in again, because there's some more things that are relevant for you. But, it took decades. So this is a tribute to the persistence of Weiss, Rainier Weiss, or Ray Weiss is people that knew him. He received the Nobel Prize in 2017 jointly with Kip Thorne and Barry Barish. Many people have heard of Kip Thorne. He's one of the most famous theoretical relativists, and he was the one that created the models that are used in the film Interstellar. And so you've seen his theoretical work and displays, and that was a supermassive black hole kind of design. In the 70s, Weiss had to pivot because of funding issues, and he wrote a proposal to the NSF as a new method to measure gravitational waves. And the idea is what's called an interferometer. But basically,
this is interesting because a lot of people came from this project, right, the Super Collider in Texas. That is also what happened with Jeffrey West. Do you remember? He was actually, it's interesting that a lot of people, it was a pity that they closed that project, but it allowed a lot of people to go in other interesting fields,
So people who don't know, there was, the largest collider now is in Europe. and at CERN, but there was a proposal in the US for one in Texas, and they even started building it, but then it got canceled.
Mm-hmm.
And so, you know, people had to find other work, and some of them went into this field. So what Weiss said, that instead of building, you know, these big aluminum bars that had to be cooled below liquid helium temperatures, to instead use lasers, but very long arms. So you have to have multi-kilometer scale arms, and the ones that got built in Louisiana and Washington State as kind of copies of each other are 4-kilometer arms. He built prototype in the 70s, and the NSF LIGO project, Laser Interferometer Gravitational Observatory, was turned on in 2015. And you see the first signal here, the first detection was on the 14th of September. It was on the third day. It was turned on the 12th of September.
No. So
Huh?
this was
the first full observing run, right?
No, there were runs much earlier than that. This was the more advanced level. You know,
this was the first
LIGO 2
LIGO 2 run, right?
Yeah, but LIGO 1 was already operational in early 2000.
But no detections.
No
right?
detection, yeah.
And then when they upgraded,
many people were saying we will never see them. You know, this is a failure.
Yeah.
We spend almost $400 million. You know, because this is a weird field because you know the detection attempts started in the 60s, like you say, and for 40 years nothing was seen, right? Besides the crazy claims from early crazy claims. The real, you know, when people started to build realistic detectors, cool down, etc. Like my advisor, for example, he spent his entire career. He retired more or less when LIGO 1 started to go on, and he spent like 40 years career without seeing anything.
Right.
It's crazy. And in fact, whenever we made conferences, there was always a sociologist that follow the field, and he will present at the conference because he studied this crazy field where we were hundreds of scientists working and no detection for decades and decades and decades. You know, like it's like if you think you need commitment for Bitcoin, you know, because it's a long-term game. Imagine this game, you know, that you play over decades and decades. And finally, you know, you got the jackpot because, you know, this was one of the most important discovery in the entire history of mankind.
Yeah.
And why is it important? Because basically is the first way, the first type of radiation, right? We see the universe not just through electromagnetic radiation, so radio waves, electromagnetic, but they are all basically the same type of radiation, right? Electromagnetic radiation. There is a huge difference between X-rays and radio waves in terms of energy, etc., but they are basically the same phenomena. And then, you know, we get particles like we detect neutrino, we get other type of particles that we see, cosmic rays, but not another type of radiation, right? That is so radically different. And this is the first time that where it's almost like the analogy will be you're watching this TV show and you don't have audio. And finally, you get this new type of information that is audio. And you can see how much more, imagine watching a YouTube video, you know, without subtitles, only pictures, and now all of a sudden you turn on audio. That is how important this discovery was. It's a completely different way of observing the universe using a completely different medium than light.
Right. So this is showing that signal that was, they didn't announce it until 2016 because they had to do a lot of data analysis and modeling, and they want to make sure they had everything right. So it was announced early in 2016. And already they got the Nobel Prize in 2017. That's how important all of this was.
Exactly. Because usually it takes many years to get a Nobel Prize from the discovery. When they award it almost immediately after the discovery, means it is recognized by everybody as something super important.
And very profound. And the two different sites, they saw identical signal. So you can see those waveforms look the same. and it all takes place in a fraction of a second. It's 0.2 of a second basically that you're seeing here.
And there is a similar detector in Italy near Pisa,
right,
where Galileo was teaching it. That one is called Virgo, and is only 3 kilometers, but almost same sensitivity.
Right. And it's interesting, the frequencies here are, frequencies that you can hear with the human ear, so you can do sonification as well.
Yeah, it sounds like something like that.
And then you see the model, and the model fits really nicely. That's the red line, the numerical relativity model. So we understand quite well what's happening, and then we can determine the masses. So what's happening is two black holes are merging with two masses, and then you have an output. We'll get to that in a second. This was an earlier, theoretical paper. Giovanni was the first author. This is from 2003.
Yeah.
And this was on the
full April Fool Day.
Okay. Well, in fact, the paper has not yet been proven out, but it was talking about the detectability of gravitational waves from neutron stars and remnants of supernova. And one of the most important supernova that's happened in recent decades is this one that happened in 1987 in the Large Magellanic Cloud. And because it was relatively close, we've got this very nice picture, taken last year that's showing the material around the compact object in the center, which is thought to be a neutron star. And the hope is that eventually we'll be able to detect the gravitational waves from these as well, but we're not sensitive enough yet.
Yeah, because so there are different type of sources. So one is when you have two large objects like black holes or neutron stars that merge, and the other ones, and in that case, it's a one time phenomena, right? So usually, even if it takes maybe millions of years for them to merge, you can see only the last few seconds. There are gravitational waves that are big enough to be observable only the last few seconds when they merge. And so, but once it happens, you have to wait for another event somewhere else, another system to do the same, right? And hopefully there are enough of these events. They are rare, but the universe is big enough where you see few of these events a year. But then there is a particular source that is what I specialize, because, like in medicine, everybody finds a focus. My focus was on continuous sources. So supposedly, if a neutron star itself has a little deformation, like because you cannot have a gravitational wave from a perfectly symmetric object. You have to have a little bit of a deformation that goes away from perfect symmetrical distribution of mass, like a little mountain, even like a centimeter tall mountain or something like that on a neutron star, because neutron stars are weird stars. So they have a solid crust that is really weird, made of neutrons. So if you have a little mountain or a little bit more mass accumulating in some region of a crust, then you can get a gravitational waves that are very, very weak in comparison to these other sources that we mentioned before. But the beauty of it that they are continuous. You can see them all the time. And so you actually can accumulate signal by adding this signal in a coherent way, and that makes the signal bigger and the noise smaller and smaller. So that is the main idea. Because they are so weak, the signal, if they exist, they are so weak, we don't see them again. So most of the research that they did in this field was, okay, given the sensitivity we have right now, we can tell that the gravitational wave cannot be higher than this. That means that the deformation on the star is no bigger than that. So, for example, we were able to tell that there are no, I don't remember exactly, but no mountains bigger than a centimeter in any of these neutron stars that we observed. That means it's incredible, right? You have a 10-kilometer wide object, and the tallest deformation that you could have, it's less than a centimeter.
Right. Yeah, 10 kilometers is a typical size. So these are very, very compact. They're the size of a city. Not quite as compact as a black hole. If you threw some more mass on it, you could get a black hole.
Have you ever read that book called Dragon's Egg? It's written.
No.
It's a science fiction book written actually by an astrophysicist, and it talks about this spaceship that goes near a neutron star and they find life, and life is made by these little creatures that put together neutrons. They are made of neutrons, basically.
Oh, okay.
It's really cool because it's talking about the relativistic effects on the neutron stars, like times is going very slowly there, right? Very fast, and so like few years for them is like centuries for us, so something like that. Like in Interstellar.
Yeah, no, it's going very slowly because of the gravitational field. Yeah. Great. So this is the first merger detection, and it was two of these intermediate class black holes. One, they measured it at 35 times the sun's mass. We call those solar masses, 35. The other one, 30. And then you put the two together, and lo and behold, when you form the single successor black hole, it was only 62 solar masses. So 3 solar masses disappear entirely, get converted entirely to energy in the form of gravitational waves. So these are extremely efficient conversions of, according to E equals mc squared, right? And at the very last few milliseconds, the source is brighter than, all the stars in the universe, just for a very, very brief time. A couple of small power laws. One, somewhat counterintuitive, is that the radius of a black hole, what we call the event horizon or the Schwarzschild radius, R sub s, is proportional to the mass. And it's simply 3 kilometers times the mass. So these would be 100 kilometers in radius before they combined, and around 180 kilometers for the black hole itself after they combined. It also depends on angular momentum. You get an oblate spheroidal kind of shape. It gets more complicated, but it's roughly like that. The radiation comes from the quadrupole moment. That just means this, it's not a single sphere that's perfect, because that doesn't have a quadrupole moment, but you've got these 2 objects. And so between them, it's the quadrupole moment that determines the luminosity. And from that, you can get the time to merger. And the time to merger is a power law. It's a power law of 2 things. One is the separation, which is A here, and it's the 4th power of the separation. And then in the denominator, it's the 3rd power of the radius of the black hole. And that is proportional to mass. So it's going something like the 4th power. There's a complication of reduced masses, but it's something like the 4th power of the separation. So it gets very, it spins up very rapidly in the last few phases, spins around, the orbit gets very tight. This one was detected from over 1 billion light years away. And as Giovanni mentioned, gravitational waves propagate at light speed. And this has been confirmed with other experiments. I don't know if I can watch this video or not. Let's see if it'll play. Well, that doesn't help. Try one more time.
Yep, it's beautiful.
There we go. So 30 and 35 solar masses.
And what we are seeing is the 2 masses are coming closer and closer, because according to Newton, right, if it was just a Newtonian physics, they will rotate forever at the same distance. But we are producing these gravitational waves that are disturbances in the space of time. and this carries energy. So because the system is losing energy, the two masses are coming closer and closer together.
We're starting the 28-day AI challenge for beginners over 40.
Sorry.
Just 15 minutes a day to level up. In 1 week, you'll feel
Something
unstoppable.
else
In 2 weeks, you'll have your
is
strategy.
going on.
In a month, you'll wonder why you didn't start sooner.
Okay, I'm back. Something else opened up in Safari. Let me run this one more time.
And the distortion we see is because light is bending from the faraway stars in these regions with high gravitational fields.
So that's what we call gravitational lensing, and it's actually used a lot now because not only does it distort an image, but it can magnify an image, and we're able to discover distant galaxies with James Webb and other space telescopes simply because they're getting some very strong magnification by their foreground clusters.
And what you get in the end is just one big black hole.
And the gravitational waves that propagate all the way to Washington State. Okay.
That's crazy, huh? And just to give a feeling for people, and I'm sorry because I could talk for hours and hours.
I know you could.
When we arrive here to Earth, what do? These gravitational waves? They stretch space and time, right? They make everything smaller and longer, and the oscillations are basically the frequency of these events that are usually in, like Stephen mentioned, in the kind of auditory range. So they are up to, from few times per second all the way to thousands per second. And so you have this oscillation of a fabric of space and time. So, because according to Einstein, space and time is not rigid, but you can squeeze it and stretch it, right? So everything, included us, car, houses, Earth, get squeezed and stretch. Now, by how much? that is a crazy thing. So we are talking about when I was working at LIGO, now it's improving, but just by a factor of maybe 10 or 100 at most. We are talking about deformation on the order of 10 to the minus 21. So whatever you have is distorted by a factor of 10 to the minus 21. That is a 10,000 of a billion of a billion, right? Just to give you an idea, the nucleus of an atom is 10 to the minus 15 meters, sorry. So we're talking about, so if you have something that is 4 kilometers, we're talking, and we're talking about a deformation of 10 to the minus 21, we're talking about a plus or minus, basically the detector says, oh, I'm seeing something, I see some stretching on this arm of a detector, and it is 4 kilometers plus or minus 1,000 of a nucleus of an atom. That is the level of precision of these devices, and that is the tiny little effect that we see coming from these huge big distances. So when you see this oscillation that we show you the graph that we observe, we're talking about deformation on the order of 1,000 of a nucleus of an atom over a distance of 4 kilometers. It's really science fiction. It's like beyond imagination that we can do crazy things like that. It's unbelievable.
Yeah, and these LIGO detectors at these two locations, they have perpendicular arms, so they want to be able to detect the compression and expansion in both directions. So they have these arms that are transverse to each other. There are a couple of other observatories. There's this Virgo one in Europe, based in Italy. It's a European consortium, and then the Japanese have one called Kagra. I guess the Chinese are building one. I'm not sure the status of that, but this shows
India, Australia.
India's doing one. Yeah. And they collaborate in order to get better signal and confirm each other.
And they are supposed to build one in space too.
Well, the long-term plan would be to put one at the Lagrange point, and you'd have 3 separate satellites, well separated, held, in a static location at the Lagrange point in the Earth-Moon orbit.
So the holy grail of all these things, and the one in space is the one that can do that in particular, is to detect the first type of information that we can ever get from the Big Bang itself, because all the information that we get now, it's cosmic radiation, and that cosmic radiation was it kind of detached from matter 300,000 years after the Big Bang. So it's a kind of like is a picture of a baby, like an infant, but you don't have a moment of birth. And so if you want to have a moment of birth, you cannot use light, because light was entangled with matter until 300,000 years after the Big Bang. You have to use gravitation, because gravitation detach from matter very, very quickly. Basically, like, I don't remember exactly, but something like 10 to the minus 45 seconds or something like that.
Certainly before 10 to the minus 36, yes.
Yeah, so 30, something like that. A very, very small little fraction of a second after the Big Bang itself. So that will be, if we get a picture of that, and we make a map of the sky of this radiation, gravitational radiation, then it's almost like we took a picture of the Big Bang itself. And that will reveal a lot of things, probably new physics that we don't have right now, because it will reveal the secret of how gravity and quantum mechanics can work together. That is one of the things that is kind of like the holy grail of physics right now. And if we get that picture, there will be a lot of information that maybe can give us clue on how to unify quantum mechanics and general relativity. So it's the biggest holy grails of all, if we could get that. We are not there yet, but eventually hopefully we will.
Yeah. So this graph is slightly more mundane than that, but really not mundane at all. And all of these blue dots are mergers of black holes, and therefore detections of black holes. And it's a log chart on the y-axis, and there's no axis on the x-axis. It's just a bunch of things laid out so you can visualize it. But they're laid out in terms of there's a left side and a right side, but they're just arbitrarily putting the highest mass and the next highest mass on one side or the other. And what you see is that the blue dots are all above 5 solar masses and go as high to above 200 solar masses. And these things are triplets. So you'll see 2 blue dots and an arrow up to a third blue dot. And so those are the 2 individual black holes, and then the combined resultant product black hole that they merged into. And they call this the stellar graveyard because now with gravitational wave astronomy, we've detected all of these higher mass, what we call intermediate mass range black holes. The red dots on either side are black holes that were detected more conventionally from the electromagnetic radiation that comes from their accretion disks. Here with gravitational wave astronomy, we don't need to see an accretion disk. We have to see that moment of merger, but we don't see the accretion disk. And so it's a completely different way of detecting black holes. And it's allowed us, they used to worry, where are the intermediate black holes? And now they've all, many have been found. The yellow dots down at the bottom are neutron stars detected electromagnetically. And then the orange ones are neutron stars that have been detected by gravitational waves. And you see there's some that are mixed because they're not quite sure whether the product is a neutron star or black hole. But
so what are the x-axis supposed to represent?
X-axis doesn't represent anything. It's just used to spread these all out so that you can visualize.
Yeah. Symmetrically, okay, somehow.
Yeah.
Yeah.
Okay. So we've got the stellar mass black holes, which are below about 10 solar masses, basically, in the 3 to 10, because 3 is kind of minimum. And then we've got the intermediate mass range. It actually can extend up into the thousands and tens of thousands. And then we're going to go on to supermassive black holes. And that's when you get into millions and billions of solar masses. And the general idea is that very early on, you could have quite massive stars because you didn't have any other elements besides hydrogen and helium. And that allows you to form larger stars. And the large stars evolve very, very rapidly. They could be a couple hundred solar masses. You could have early clusters. You could get formations of large intermediate scale black holes into the thousands, and then they could combine with each other, and eventually, you'd get a supermassive black hole. The details are not very well known because we don't have a lot of observational data but that's the general picture, and that would happen preferentially at the core of galaxies, and so you get a dominant supermassive black hole in every galaxy. Now, the supermassive ones we've only detected electromagnetically, not through gravitational wave mergers. We haven't seen any mergers of those. These photographs are of two different ones. One is 4 billion solar masses, the other is 4 million solar masses. And these are actually taken in the radio, about 1 millimeter wavelength. And they use a network of about 10 radio telescopes around the world, including locations in Hawaii and Arizona and Chile and Spain, Greenland, and even at the South Pole. And that little image shows that they do the observations, they have atomic clocks, so they have very tight timing. They do initial data reduction, put it onto disk drives, and they fly the disk drives to one location. And they put all the disk drives together in one computer and correlate all the signals.
Mm-hmm.
And by doing that, this is called aperture synthesis, or very long baseline interferometry. And what they can do is, with this event horizon telescope that it's called, when it's used as a collective thing, they get the effect of that very long baseline, and so they get very high angular resolution on the source, and that's how they're able to get images that are so good.
Crazy.
Now, M87 is much further away, but it's also much more massive. It's 4 billion solar masses. It's a very well-known active galaxy. It's got this huge jet coming out of it, and the asterisk means the black hole, as opposed to the M87, which is one of the original Messier galaxies.
Right.
Very well known. The other one is the black hole at the center of our own galaxy, at the Milky Way. It's known as Sagittarius A star. Sagittarius A refers to a dense stellar region in the core. This one has had stars detected in orbit around the black hole, and we've been observing those for many years, and so we have a sense of how those orbits are progressing, and we can use that to help constrain the mass and to determine the mass around 4 million solar masses. This radiation is not thermal radiation from the accretion disk. It's called synchrotron. It's basically electrons that are being accelerated in strong magnetic fields. There's the source of this non-thermal radiation. Now, these kinds of objects all go under the umbrella of active galactic nuclei. There are many types: quasars, quasi-stellar objects, Seyferts, VLAC objects, and others. The quasars are the most energetic category, and typically were discovered in radio emission. Now, this is a chart of how these different classes, in particular the luminous quasars, but also moderate and low luminosity active galactic nuclei, how their density is changing as a function of the age of the universe. And right now, the age of the universe is 14 billion years, 13.8, determined pretty precisely from the cosmic microwave background and other methods. And so we've got a log linear chart of the density versus the age. And that density is correcting for the fact that the universe is expanding. It's called the co-moving density. So it's just the density within the same volume as it expands. And what we see for the orange curve is that it rose during the first couple of billion years. It flattened out around 3 to 4 billion years, and it's been in decline ever since. And the density of these highly luminous quasars is about a factor of 30 lower today than it was at the peak, which is called cosmic noon. The others, they also rose, flattened out. They've had perhaps a more gradual decline for the moderate ones, and still the low luminosity.
So their density is a function of how many stars we are,
How
much material they are absorbing.
Material.
Yeah.
They are being fed by material. It's primarily gas, not stars. And so over their history, these highly luminous phases called quasar phases, there might be of order 10 of those for a high mass supermassive black hole, say 1 billion solar masses. And then these lower luminosity Seyfert-like phases are more numerous, and so they're still going on because you don't need to feed as much material. These bright phases are a relatively small percentage of the overall time. So they're mostly in quiescence. Our own Sagittarius A is in quiescence. You know, we're just seeing the luminosity from the accretion disk from sort of more continuous kind of flow into the black hole, but not high volume flow. So it'll flicker for maybe 10 million years, 100 million years, you know, spread over some dozens of episodes or fewer if you're talking about the highest luminosity one. And the variation in luminosity is incredible. It can be millions or billions of times brighter. And this is shown in the histogram here. First of all, on the left side, there's a pie chart that indicates that about 85% of the mass inflow into these objects is cold molecular gas in the core of the galaxy. And that eventually gets exhausted. Some of it is due to the natural mass loss from stars as they go through their evolution. And actually only a small percentage is due to stars or clusters of stars. And then in the histogram, we see for 4 different masses, the 4 times 10 to the 6 is the same as the mass of our own galaxy's black hole. And then we see 100 million solar masses and 1 billion solar masses. And you're looking at the luminosity there, and you can see it goes from 10 to the 37th up to 10 to the 47th. You know, it's a dynamic range of 1 billion times increase. There's a natural limit. It's called the Eddington limit as to how much eventually the radiation pressure holds back the material and the thermal pressure within that accretion disk. And so these things have a natural kind of quenching limit, but it's at a very high velocity. Just to give you an illustration, you know, the luminosity of our sun is 3.5 orders of magnitude below that 10 to the 37. So even in their quiescent phase, these are quite luminous. So here's my analogy with Bitcoin, is that we've had this history when we had these very powerful flaring, but that's dying out over time. And we can equate a Bitcoin year to about 830 million cosmic years, given the universe's age of 13.8 billion years. And then, you know, we're just showing the linear relationship on the large chart here. And we've just picked off some kind of typical phases or times where we had the rise around 2 billion years of age, which is like 2 years of age for Bitcoin. And then 4 years, 5 giga years, around 4 years for Bitcoin would correspond to the 2013 bubble. The 2017 bubble would correspond to when the universe was about 9 billion years. And by then we're already in declining activity, especially for that orange line in the inset chart for the very luminous quasars. And then more decline as we get to the 2021 bubble, lower accretion into the black hole. And by now we're clearly into a quiescent era where the largest bubbles have faded away. The mass growth from one of these events can be a few percent of the mass of the supermassive black hole, if say it's 100 million solar masses or a billion solar masses. But in the most energetic ones, it can double its mass because it may go for 50 million years and it may be accreting, something like 20 million solar masses of material per year. And so that all adds up to a billion years for that particularly relatively short event. And this shows it with the Bitcoin epoch candles. We've kind of had these 5 epochs. We're into the 5th epoch, and correspondence with the cosmic ages of around 2 and 4 and 7 gigayears, which is a billion years. And where we've got fewer flares by, the life going halfway through the life, basically at 7 gigayears, which would correspond for Bitcoin at 2017. And that, we had the biggest bubbles in 2011, 2013, 2017, and since then it's been dying down. And things are moving more towards a quiescent era. And this shows it with the major bubbles and the mini bubbles. There are 31 mini bubbles here, and I've shown this in the past in previous Physics of Bitcoin shows that we've got fewer and not as many clumping together to give the major bubbles, and the energy of these has gone down. So it's as if we had less retail gas feeding the herding behavior and the FOMO behavior relative to the capital needed to fuel a kind of flaring event or bubble event in Bitcoin. This black box shows this duration of a very bright quasar event, 50 million years. Maybe it consumes 22 solar masses per year, and then you'll consume a billion solar masses in that event. So if you started out with a billion solar mass black hole, it could double. And that's somewhat analogous to what we've seen in terms of Bitcoin, could rise in price factors of 10, factors of 5, factors of 3 and 4, but now it's getting smaller and smaller. So you have this in the lower part of that black box, these shorter episodes. Maybe they last 10 million years. Maybe the accretion rate is only 1% of the other one. And so the gain in the mass might be only a few percent. So the idea is that the coal gas supply is mostly exhausted in the cores of these galaxies over several billion years. More stable inflows continue from the inner edge of the accretion disk. And for our own galaxies, Sagittarius A star supermassive black hole, you're only getting about 5 to 10 solar masses per billion years to fuel the luminosity that we see now. So that's analogous to more of the kind of institutional behavior where you have longer term holdings for Bitcoin. Now, I think you can say that this black hole analogy is kind of dying out, right? Because it's saying less bursty, less flaring, more consistent laminar flow. So then the question is, what's fueling things? And I've argued that now increasingly Bitcoin is fueled by institutional holdings in both the treasury companies and the ETFs, and those have been rising as the fourth power or faster of Bitcoin age. And so I'll make a different analogy, which is dark energy. We don't have time for that this week. I will go into that in next week's Physics of Bitcoin.
This is so cool. And also because it gives us an opportunity to talk about cool physics.
Yes. So and honor people like Rainier Weiss,
Right,
and their contributions. So I will close with the latest in the log periodic fits that I ran in the last couple of days. First, Bitcoin, the 2-year chart, and it's projecting continuation into the end of March and a price target of around $174,000. And it's a good R-squared, it's 0.96, so it's quite a nice fit. And the upper chart just shows the split between the kind of long-term core and the more bubbly zones and the transition zones in yellow. And then the upper chart is the 1-year fit, and that's discordant from the other one. It's saying that peak would come in about 3 or 4 days, and it would be around 119,000. The R squared is still pretty good, 0.94. This is band, this shaded blue band is a 1 sigma uncertainty of $5,700. Now we've fallen below the band, but you haven't broken unless you fall to 2 sigma, and we're still between 1 and 2 sigma. So we can't obsolete this chart yet or deprecate it. We just have to follow it and see if we get restoration. If you go to 4 months, you don't have as good a fit. R squared of 0.72, you can see that it doesn't have multiple waves to fit, so it's more uncertain. But it's projecting into November at around 114,000. So these two are broadly consistent with each other, I suppose, but they don't allow us to project for a long-term, going through 150,000. They're projecting some kind of breakdown, in the short term, maybe during this month of September. And then I'm closing with 2 charts for master strategy, a 2-year chart and a 6-month. Now, remember, these are quite different because this is trading on a stock exchange 32 hours a week. You only have 1/5 as many hours per week of trading. And so a 2-year doesn't have as many data points, or a 6-month doesn't have as many data points as a Bitcoin chart would. And you have to go to hourly for the 6-month curve. So the 2-year with a good R squared is showing a very rapid ascent into the end of November with a 789 price target. I think it closed at 330 yesterday for master. And of course, the price is already broken down. It looks like it's approaching the 2 sigma, but it hasn't quite hit the 2 sigma. And then we've got a discordant result with the 6-month chart using hourly data. Its R squared is not nearly as good. It's 0.69. It has a much lower frequency, so not as many oscillations, and it can't therefore carry as high. In fact, it flattens out because of the recent breakdown. But again, it hasn't broken the 2 sigma level, just the 1 sigma level. But it is saying that we're just peaking like now. And that it would have been $400 3 days ago, and we clearly didn't reach that. So we're kind of at a crossroads in both Bitcoin and in strategy between the intermediate term and the longer term charts. Longer term for long periodic, which isn't meant to look out over years, but just many months. We'll have to see how this resolves, whether it breaks the 2 sigma or whether we can get a bounce here and restore some comfort towards a longer term projection. And I will close with that and note that Bitcoin volatility has plummeted from around 60% at the beginning of the year to a current record low of 30%, consistent with my analogy with supermassive black holes.
Very good. Okay. All right. And we can answer questions later. I will show my work for this week. So basically, I'm continuing this work on this idea that I kind of introduced last week, but it went a little bit deeper. So let me see, first of all, if I can get back to... Is this better? Does it show does it improve no? Stephen? Stephen? Are you still there? I cannot hear you. Oh, Stephen is gone. Okay, I will try to share the screen. I was asking Stephen for feedback. You guys can tell me in the comments, but I'm trying to make the screen bigger. So I'm going to summarize a little bit what I discussed last week and show new results. Okay, so the main idea is that we're looking at the returns, because returns are one of the best way to understand a financial asset. Now, and there are, if you look at the financial literature, there are thousands of papers trying to model returns of different financial assets, right? The usual expectation that these returns are constant in time, because if not the returns itself, but the logs, because the returns itself, because if you have an exponential growth and most financial assets, gold, stocks, etc., they grow exponentially, and mainly due to inflation. A little bit because of productivity increase, but a large part of their increase in time is illusory. It's due to inflation. And so the definition of an asset that grows exponentially is that the returns are constant in time. So you will not expect, you can characterize, right? You can try to do a distribution plot for maybe like in a moving average, or maybe looking at different times, like 5 years ago, 10 years ago. But usually the idea is that we are constant in time. So you can talk about one single distribution of the returns. Now, with something like the power law, if you are assuming that we are having the price follows a power law, you're not expecting constant returns. They're actually a function of time. So you can express return as the difference in price between two different times, like actually to express it as a ratio. It's basically the same thing. So if we take a ratio, right, if this is the formula, this is what following a power law means, right, that the price is proportional to, in this case, time, to some kind of a power. We know that power is close to 6. Then you take the price at two different times, P2, the price at P2 and P1, at time T2 over T1. You can take the ratio of these two, and then you can see it can be written in this way, right? Now you can take the log, the simple laws of the logs is that if you take the log of a power, the power goes down, right, like this, becomes a multiplicative factor, and then basically the log of a return is equal to some constant times the log of this ratio in time, where a time is measured as time from the Bitcoin Big Bang, if you want to do another astrophysics analogy, the Genesis block. Now, if you're looking at daily returns, basically the difference between T1 and T2 is only 1 day. So it's basically, this is today and this is tomorrow, right? Or yesterday and today. So it's simply T2 is nothing else than T plus 1. And I can drop basically these indexes, right? So you have only time and T plus 1. So basically the log of the returns, again, it's easier to play with logs when you study these things. Everything kind of linearized in that way. So the log of the returns is equal to some constant times this function of time, right? I don't know how to characterize this. It's kind of like an hyperbola, maybe, but not quite. Maybe yes, right? Because if I rewrite this as a I divide these by t. I have t1 plus 1 over t. So it's kind of like an hyperbola, right? Plus a constant. So this is a diminishing return function. So why is diminishing? Well, because you can see, right, as t becomes bigger and bigger and bigger, the difference between t and t plus 1 is smaller and smaller and smaller. Basically, t kind of approaches, t plus 1 approaches t, right? If you have a 1 million plus 1, it's basically like 1 million, right? So as you make this number big, it's not that we are going to see a million, because it will be 1 million days from the Genesis block, but just to give you an idea, right? As this number becomes bigger, this number tends to 1, right? So it starts relatively large, and then it goes down, basically never becoming 1, but approaching 1. Now, what happens is, if you plot these guys over time, so this is what theory says, right? So if basically these, I'm kind of repeating what I said last time, but it's so important that I want to explain this one more time to people. So this is what the theory says, right? So it's another way of testing if this idea of a power law is real. Because many people criticize the fitting. They say there is something fishy. Maybe they are not used to do this fitting in the log law space. So many people are not super convinced by fitting in log space. But here we are just saying, assume this is what we are expecting. There is this kind of temporal behavior. The returns are not constant. They should be a function of time. And in fact, the returns should go down in time. And then you simply say, okay, let's plot the real returns, right? The daily returns. How do they look like? They look like these. It's very difficult to see because, we have these large returns in the beginning. We will have to zoom in. But if we zoom in, you can see there is a very precise trend. Of course, it's a statistical thing, also because we have the bubbles where the returns are bigger, etc. But it's clearly going down. The red curve is that theoretical curve that I plotted. And you can see immediately that it does represent the general trend. It is in the middle. I don't know if you want to call it the mean. Is really, it turns out it represents more like the median behavior. But it's a very good representation of the average behavior of these returns. So it seems that the power law is something much more fundamental than just some kind of a fitting of the prices in time, right? Now, if you zoom in, you can see, right, we have very large values here, and then this is what the theoretical curve looks like. It's flattening out. Just to give you an example, right, early on, we had returns that were like 10 pair in 1 year, and now we have more like 45% in a year. And these returns will continue to go down all the way to something like 15%, 17%, I don't remember, in 20 years from now. So we still have many, many years where we can beat the stock market by power law alone, right? And Bitcoin will be basically $10 million by then. Okay, now the idea is this, right? I'm still not convinced. You say, okay, kind of it fits, it goes in the middle, but how can we show really that this behavior in time is truly represented by this curve? So one way of doing it is to take that function of time, right, and basically divide the return, normalize the return by this function of time. And if I do that, and by normalizing, I mean by dividing, we simply divide by that function. Then if I take the log and return by that function, I should get a constant. The constant is supposed to represent the slope. So it's really, if you do it for each single day, you're going to get a bunch of values. It's basically, we can call it the local slope. So we are not going to have a total slope that we observe at value close to 6 or each day, because sometimes we are above, sometimes we are below. But the idea is that if you take enough of them, their they are going to kind of be symmetric around the observed global value, right? If a power law is a good representation of a behavior of a returns, we should see values of this n, we can call it, local slopes or normalized returns. On the left, on the right, it should be a relatively symmetric distribution. And it depends on the distribution. If it was a Gaussian, then you will have a proper mean. Otherwise, you will have some other parameter that represents the equivalent of a mean. And it should be close to the global value that we observe. And if I divide by this, then the decay in time that we observe should go away, and you should see something that is stable in time. And so this is the first result, and they use different distributions. I have actually a better graph with more bars, and I use Laplace or Lenzien. Actually, recently I found another distribution is called T local scale distribution that seems to be the best type of distribution to fit the data. And you can see the different parameters, right? Even the Gaussian is not really a good fit, but even the Gaussian give us, in that case, you can calculate the mean. It gives 5.83. There are other parameters that are not exactly, it's more like the median for the other parameter. For example, for the Lorentzian, use the median more than the average 5.85. All these values are familiar to us, are basically that 6 that we mention all the time, that is the slope that we get by fitting the data. So this is a completely different method. Of course, everything is related, but you're coming from a completely different direction, and you're still getting the same value that we get by fitting the data in the log space, right? Of course, the two, if the signal is real, if the result is real, they should be consistent. But it's really interesting, right? If this was noise, if this phenomena was like overfitting, etc., you will not see this consistency. So this is really cool, because then if we have a good model, statistical model of both the average behavior, but also of a median behavior, and then the size of the deviations, then maybe we cannot reproduce the behavior during the bubble, because maybe you see here where we see this bump here, that is maybe the bubbles. We could reproduce, we could try to add this little artificially this bump, but if we stick to a theoretical model that is based on some kind of equation, etc., then what we reproduce is the average power law behavior, right? What we call the core power law behavior, and we can ignore the bubbles. And so we can test these, and we can see. So first of all, I did some different simulations, testing of these distributions. So you get very, very high R squares and very small p-value. That is, it's basically this distribution is not due to chance. And the nicest result is this one, right? So if I now normalize, basically I calculate these local slopes. These are slopes, but also basically these normalized returns, right? You get this quantity, and you can see it doesn't change in time. And it doesn't change in time, both in terms of how big the deviations are, and also its average value. This red curve represents some kind of moving average. And I didn't draw here, but 5. So if you zoom in, some of them are huge, right? A slope of 200, 400. What does it mean? Or minus 400, right? Seems amazingly big relatively to this value of 5 or 6. But if you draw a line that represents 6, it goes in the middle of this red line. And this red line is basically the oscillations around this median value. And so it's stable. You see, there is not the decay that we observe. And so this is really cool, because it means we found a value that is constant in time. It's basically is it doesn't matter what happened to Bitcoin, all the different events, all the different when it was, $20, $30, $100, $1,000, all the different things that happen, the event or ETF, or China banning Bitcoin. You have one thing consistent in time, of course, statistically, that is this quantity. It never changed in the entire history of Bitcoin. It's really, really cool. It's a powerful thing. In physics, we are always looking for what changes and what stay constant. When we find something constant, like when we find principle like conservation of energy, conservation of momentum, it's a big deal because it says, first of all, there is something fundamental at play there that characterizes the system, but also you can use it to kind of solve different problems, right? You can solve very difficult problem in physics by invoking conservation of momentum, invoking conservation of energy, and so on. So it's one of the holy grail of physics, finding what we call invariant quantities. And this is an invariant quantity of Bitcoin. It should be everywhere. I think the reason why this is not a viral post when I made it is because people don't understand it. They don't appreciate it. They don't value it. But, Stephen is here. He can, I'm sure that he agrees with me that it's a big deal to find something that is consistent in Bitcoin. And, you could have say, well, that the slope is also consistent, but this is more powerful because we're talking about the returns itself.
It's incredible how precise, with its mean at 5.8, 5.9.
Yeah.
How precisely that matches.
It's incredible, right? And then you can use it, given that you have something that is consistent in time, and you can then basically simulate these return, these the DSDs, right? I can simulate these because I know the distribution now, and none of this distribution will be a perfect match. You will find the one that comes closest to it. You can try different types, but it's a pretty good representation of a statistical behavior, and you can see it's a very, very good match. And then basically you can play this game. We call it Monte Carlo because there is this historical casino in Monte Carlo, right? The little a principate. It's like a kingdom, little kingdom near Italy. And a lot of their revenues come from this casino, where very rich people go and play. It's like kind of like classy Las Vegas type of place, and because you are rolling dice, turning roulette, etc. It's basically like a random generator place, right? And so we do this simulation in physics. We if we know the distribution of something, we can replicate. Basically, it's like a fancy dice where you use a computer to roll these dice, but instead of having just 6 sides, it has an infinite number of sides, basically. But it has the type of statistical distribution or whatever distribution you want to use. So you can basically simulate these returns, never perfect, but close enough. And then basically, how do you go from these guys that are slopes to the returns? Well, basically you multiply back that time factor. That is a deterministic thing. That is one of the big things we are saying. We are saying Bitcoin has 2 components. It has stochastic behavior like this, that is all determined by randomness. Then it has a deterministic component. Basically, you can write an equation that is that t plus 1 over t. So you multiply by that factor, by the log of that factor, and now you get a return. You get a return back. And then if you have returns, you can simulate, we have 6,000 days of Bitcoin right now, Bitcoin history. You can simulate all possible histories of Bitcoin, thousands and thousands of history, fake histories, and you can do it thousands, if not hundreds of thousands, or maybe even millions of times. And this is what they did. I produced these histories. These are all alternative histories of Bitcoin. And I color-coded them from very unlikely one. How do I know they're unlikely? Basically, I measure the density, so how many of these paths are close together. And the idea is more paths there are, more likely there are. And so the most likely paths are the green ones, and the most unlikely ones are the red ones. Are possible, but they are. It's like winning the lottery. If you go to these crazy values, we are talking 10 to the 10 means $10 billion Bitcoin, right? So there is an history where Bitcoin today is $10 billion, but it's very unlikely history. Basically, you roll the die. It's like rolling a dice in these all sixes, or a bunch of sixes one after another, right? It's very unlikely history. It happened, but it's very unlikely. And then you have, unfortunately, histories where Bitcoin is below $1, like this one, right? This history is very sad that Bitcoin is only a few cents or something.
You should give that a name. Call that the Nicholas Nassim Taleb path.
But he says it goes to zero. It doesn't even that history doesn't bring Bitcoin to zero. It's like impossible.
I think if it took this one, he would claim victory.
But he will be wrong, at least mathematically, right? Because it's not zero. But the cool thing is, well, several things, right? So first of all, this red line that it looks so familiar, right? It looks like the power law, is nothing else than the median of all these paths. So I didn't fit it. I simply took the median of all these paths, and I get something that looks like a straight line, and in this log graph, and it's the power law. It has exactly the slope of the power law, and this is the median. So basically, you reconstruct the median behavior of the power law by taking the median of all these possible paths. So one possible interpretation is that it's kind of like, remember when I was talking a few weeks ago about the principle of least action, that it's true that all these are possible paths, but some reason, and I need to think about this, maybe you can think together, there is you could say, why we didn't follow all the other paths? Why we follow this path? It's possible because really, truly, Bitcoin wants to follow the path of least action, the most likely path, that is this median. So these are virtual paths, one impossible interpretation. That is how we think about light today, right? We say, really, literally, light follows all the different paths, but all these paths cancel each other out to give you the most likely path. That is what we then finally observe, because everything else is canceled. So these are kind of like that is a crazy interpretation, but is a possible interpretation, right? That Bitcoin has in itself the possibility to go to $10 billion or to a fraction of a dollar in 15 years. But really, in the way it works and interacts with the world, it finds the path, the most likely path, that is the power law. And I like it as an interpretation. It's a beautiful interpretation. Now, the green area, you can see kind of are parallel paths in a sense, right? So the limits, they are still following the power law, and the range, it's anything between $20, $30 all the way to $1 million, right? But I really like the idea of this red line being the most likely path, and this is what Bitcoin is following. Now, of course, right, it has deviations, but then it wants to go back to this attractor, right? This is like an attractor where that Bitcoin wants to follow. So this is the history. Basically, we reproduce the history of Bitcoin, and it's consistent, right, with this approach. I really, really like this graph. It's so interesting. And this thing is called T-location scale, this type of distribution that seems to be the best fit. And then what I did, the beauty of Monte Carlo is not just to reproduce the past, but also once you are confident that it gives you a good representation of the past, you can use it to project to the future. And this is the projection for the next 3 months. And you can see again, the middle ground is the power law. basically is telling us, it will continue to follow the power law because it's the path of least action, of least resistance. But it also gives you a possible range. And usually you get these red paths if you give it enough time to, to go away from likely path. But all these seems, maybe these extremes are more reddish than these guys here, a little bit more reddish, but there is still some green stuff. So they are still likely, but they became more and more unlikely as you go away from this green area. So let's use the denser part as maybe the first range, the most likely range. And so we're talking about November, middle of November. So if we go here, we are talking about, let's say 160, right? 160. So by power law alone, we should be 110 or something like that in 3 months from now. Now I ask it to do the Monte Carlo starting from the latest points we had in the last few days. I think when I did this, we were close to 1.8 or 1.7 or something like that. If you use the middle power law, maybe we will be higher. But anyway, so anything between 80 to 160, let's say, that what is in the realm of possibility. If you're thinking Bitcoin crashing even more than 80, is basically almost impossible given the stats. Now, I did check the consistency of these stats. In fact, that is the next thing I will do. I will do a moving average of these parameters and show you that they are super consistent. So you already saw that by that moving average of a mean, basically, the equivalent of a mean. But I can also look at the spread, how consistent the spread of the distribution is over the years. And it's super consistent. It does not change. But I will have some graph to demonstrate that. So if you stick to the pure statistics of Bitcoin, without the turbulence of the bubble, that adds volatility to that. But even on the graph, we need to understand. Probably I will color code it to make sure, but it seems that it's possible that little bump is what the bubble represents. So this large deviation, like this deviation that we see. And here I'm not modeling that. So basically, I'm assuming that we don't have like a bubble anymore. So this is the behavior without the bubble. Now we could add some additional volatility to represent the bubble, but it seems that we don't see that right now. We don't see additional volatility. So it's this is where I am. I'm still exploring these things. I really like this approach because I think it really goes to the core of what is important. If we find an invariant quantity and it contains all the information about Bitcoin behavior without the distraction of the bubbles, etc. I did this prediction for the next 3 months. I also did it for the next 20 years. I'm not showing them here, but we can look at next time. So we can look at short range, long range predictions and update it as we go and compare reality with what this Monte Carlo simulation gives us. I don't say it's the ultimate tool, but it's for sure one more tool we have that is very powerful. So this is what they worked on in the last few days.
So I just fed the monthly prices to ChatGPT and asked it to compute all the power law indices month to month.
Yep.
And produce a histogram and determine the mean. The mean is 5.93.
Yeah.
For all of the monthly returns, it's the same value, comes right on top.
Yeah, exactly. And that for a gas and mean, I think you can later check.
That's just a straight mean without considering the distribution.
Right. Yeah. So later look at very, very different type of distribution.
Yeah.
See if Lorentzian, Laplace. I'm trying to look at the distribution with T location scale is basically like a T student distribution that is shifted. It seems to be the one that works best. And it's interesting because basically you don't have like a mean. It's not well defined, and the reason is because sometimes you get so large value from the tail because the tail is so big that it skews the mean. So there are some simulation where you can calculate it, and then it seems to converge, and then it diverges all of a sudden. So it's better to use a median in that case. This is why this median then is perfectly, it really shows the power law, right? I'm not drawing a straight line, I'm not fitting a regression line, it comes from the median of all the values. It is a really cool result. And so, because many times people use actually the returns to eliminate spurious trends, this shows that the power law is not a spurious trend. It's a real trend. It's a real behavior. In fact, it's at the core of a statistical behavior of Bitcoin. And we got it. We got that function that represents, because, for example, Sailor, right? And Sailor does this as a job. That is what his company does, right? From what I understand, they create financial models or whatever. And, he was against models for some time. I think he was talking about something else, but then he came out with that Bitcoin 2025, right? And that
24.
model, 24,
yeah,
was a joke because his way of modeling Bitcoin was an exponential with decaying returns. At that point, use a power law because what a power law is. The difference between an exponential and power law is that it's basically you have this 1/t time that makes the return going smaller and smaller with time. But now you are using the proper functional form. You are not shortening an exponential and creating some kind of, why will you call it an exponential if it has diminishing return, when the definition of an exponential is a process that has constant returns? That is how you define an exponential.
Constant compound annual growth.
Right.
We're at an hour and a half, so I wonder if we should go to questions.
Yes. Okay. So this one, do you think ETF and impact and the difference? You go ahead with and answer this question.
Oh, I don't know. Look, it's not the ETFs that have the impact lately. It's the treasury companies. About 3/4 of the net buying is with them, not with the ETFs.
Yeah. They are changing the game. They are not changing it. The beauty and interesting thing, they are not changing the core behavior of the power law, because, like I say, in fact, next episode, I want to show you the distribution pre and after ETF, or pre and after, for example, Sailor. We can do that. We can show the distribution of the returns before and after, and it's the same distribution, because anyway, the returns from the and we could even try to do that. We could try to eliminate the bubbles, just to make sure we don't include noise, because the bubble can be represented as noise. But the core distribution that produces the power law of the returns is exactly the same. It's not changed.
What I have done is the LPPL since the beginning of 2023, and then 2 years and there wasn't difference in those. And so that crossed the boundary of when the ETF started. Didn't see much difference.
This is another question that people ask all the time. I already answered this. Look, the only thing we can do scientifically is to compare the past and the present, right? There is nothing else that you can do, because if you start to talk, unless you have some other way of modeling what could happen, because you have some additional data, all these discussion, so for example, I had this thing called the full model, right? That where I try to attempt to represent what could have happened this cycle if we repeated all the past behavior. That is the only scientific thing you can do, that it can then replicate what happens in reality or not. But anything else that you try to do, it's just made up. So the only thing we could have done is exactly what I already done, that what say, look, we see this irregularity, the peaks seem to happen all the time at the same time. Now, we don't have thousands of data points. By the way, even if we had thousands of data points, it doesn't mean that 1001 does what all the other 1,000 data points do. It's possible that you reach a certain point where, you had all this irregularity, and all of a sudden you don't even have a peak at all, because we have some kind of regime shift, and so we don't see the things repeating like in the past. Because right now, if we were following the same script, we will be at 150, 160. We are not there. So something is peculiar about this cycle. Now, are we still seeing like a mini top where we don't go to 200, maybe we go to 170? We don't know. We need new data. We don't know how we are going to behave in this new regime. Something is different. We can see it. And that is part of why it's good to make these models, because when things don't follow the model, then you can say, well, this is what we should have done. We're not doing it, so something is different. So models are useful even when they don't work, when they fail, okay? Because the purpose of a model is not just to predict the future, but also to compare what is supposed to happen with what is happening. Reality always wins, right? So we need to, that means what? It means that something changed. We're not repeating what happened in the past, all that regularity. Now, is it an anomaly? Are we going to see a normal cycle, right? Remember, in that case, we will still see a relatively small peak, because part of a regularity of the past was this very precise decay. The decay will be even bigger in 4 years from now. But it's possible that we go back to a regular cycle next time. We don't know. Maybe this is peculiar, and next cycle we go back to business. I don't know. We don't know. We need to accumulate more data. So the only thing we know is what changes and what stays the same. What stays the same? The power law. The power law, so far, if anything, is stronger than ever, because actually, when we left the power law during the bull run, that was a challenge to the power law. The only reason why the power law was restored is because we went up as much we went down. And the two paths of going up and down cancel each other, leaving the power law. But if you don't leave a power law, you stay on the power law is even stronger. So we are following the power law, and there are many ways of measuring that. The distribution, you can calculate the R square. R square is becoming stronger instead of becoming weaker. So that stays the same. That doesn't change. The cycle is different. So when you're saying, well, maybe the top didn't happen, it's not going to happen in November, it's going to happen in February. Based on what? We don't have any precedents for that. So anybody that makes that claim is making some conjecture or some basically guess. And we don't like to do guess. So I don't have anything to say about tops happening in February, March, next year, in 3 years from now. We don't know. The only honest thing that you can say is that we need more data. We need to see what is happening, and we can compare what is happening now with what happened in the past. And by doing that, we can say it's a different type of cycle. Hopefully this. Now, the other thing is this drop, right? If we don't have a top, are we going back to the what we call the power law support line? We don't know that either. There is no law in the universe that says that should not happen. Now, it's possible that this going back to that support line was an overreaction to these bull runs. And so we went down to that because we were overreacting, given that we went, 5 times, 10 times away from the power law. The question is, if we don't go away all these multiples of the power law, are we going down? Are we going to see huge big correction? We can make a guess, and my guess, if I had to make a guess, is no. I think maybe we just simply stay on the power law for the next 20 years. And you know what? If that happens, I will be okay with it. I will not complain. What do you think?
Well, I think the distinction between the bubble regions and the core is going away, right? Or it's becoming less with time. Yeah. The volatility in the core has not changed. It's been consistent.
Exactly.
But the volatility in the bubbles has come down considerably and is now should be around 0.2 or a little bit less in the log. And so overall, we're in the mid 30s for volatility between those two sources. And so I think we may just be converging on something that has that kind of volatility for a while. It maybe become much harder to show a distinct bubble region. We'll have some of these small flares and small mini bubbles, but maybe no major ones.
Yeah,
is my guess, but yeah.
And that is fine because, I know that some people will find it boring. I don't see what is boring because we will still have oscillations. We go down 10%, up to 15%, look, I'm not in Bitcoin because I'm going to have a kind of a roller coaster experience. I can do other things to have a kind of excitement. I want to have something that I can rely on, and if he follows the power law and he stays there, I think institutions will feel more confident. It will be very weird to have a investment that is so predictable and that is reliable. It's a kind of a standard that people will still not believe it, because I'm sure in 20 years from now there will be people that still refuse to look at these graphs. They still refuse to understand the power law in 20 years from now, right? I think more and more people will realize what is going on and will accept it, but there will be still people that maybe they don't understand the math, maybe I don't know, there is some kind of mental block. But for us, for people that get it, it's probably the best possible path, because there were a lot of bad things associated with the bull run too, right? There's some good things. We got a lot of media attention. The retailers got attracted. The grandma all of a sudden wanted to buy Bitcoin. But you know what they say, when grandma is telling you about her investment, it's time to get out, right? That is one of the best indicators that we reach the peak. But so many people left Bitcoin. Nobody's in. Even if you bought at the peak, at the last peak, you will be in positive. The problem with that is that there are a lot of people that do buy at the top. They get scared because they don't know Bitcoin. They don't understand this idea, that Bitcoin goes up anyway over time. And they sold, they lost money, then they don't come back. And a lot of people were in that group, So if we don't have that, maybe it's a good thing in general. But, we are playing a different game. It's not a matter of retailers anymore, like Stephen said. It's mostly these treasury companies. It's now a different type of scale game. And so, retailers are still important because, of course, we want more and more Bitcoiners joining in. And
We have more and more Bitcoiners. It's just
Yeah.
they're shareholders in strategy, and they're the owners of the ETFs that are being held custodian for them. It's made it easier for them to buy.
Exactly. So so I think it's actually a good thing if you're gonna have bubbles. They were part of Bitcoin history. They need to be understood, characterized if you want to do history of Bitcoin. But in terms of the future of Bitcoin, it's good if they're not here anymore. Or maybe we will have mini bubbles, and then we will have to characterize them in a different way, understand them in a different way, and so on. We need more data. Anyway, I think this covers most of the questions, the relevant questions. So, and so we almost went for 2 hours. We covered a lot of interesting topics and physics. Don't have physicists talking about physics because they can do it for days and days and days. It's our first love. Anyway, good night, everybody. At least for us in US. Good morning.
Yeah, and good day in Asia, and good morning in Europe.
Next time. Bye, everybody.
Goodbye. Thank you.
Bye.